very easy. Let's go to question 5, which is 12. So let's look at question 5. So question 5 says, a block of inertia MB is attached to a very light string wound about a uniform disk of inertia MD and a radius RD. The disk rotates on a horizontal axis as shown. You may take the rotational inertia of the disk to be ID is equals to half MD RD squared. You may neglect air resistance and ignore any friction force exerted on or by the axon. And then they say the first question, why must a point on the outer rim of the disk have the same speed as the block? And then part B, okay, I removed part B because part B was just theoretical again. I want us to look specifically at part C. If the block is released from rest, what is its speed after it has fallen a distance d? Fine. So I want to sort of go into the theory around this issue of rotational inertia. Right. So what we know is that I want to take you back to the issue of torque. I'll start with torque. So let's say we have our object. Okay, let me take a simple one. Let's say we have an object that is like this, and we have an object at the end of this lever arm, and then this is our central point at O. Let's say this object has a mass. Let's say the mass, which is equals to m kilograms. Let's assume that we put a force of F, and then we know that this radius is R. We put a force of F on this object, right? So what we know is that the torque is given by the distance times the force. So it's basically the distance from the central point multiplied by the force. And usually we usually write it as R multiplied by F sine of theta. The reason why we do that, we put sine of theta because the force may be at an angle. So assume that the force was at an angle, let's say of theta from the lever arm. In that case, we would then put sine of what? Sine of theta. Why do we put sine of theta? Because we want to have our force to be what? To be perpendicular. Because let me try to explain this idea here in a better way. Let's say we have our central point here, and then we have our lever arm, and then we have our force that's going this way at an angle of theta. So I can take this force and put it as two components, right? Resolving forces, I can have F sine of theta, and I can have F cosine of theta, right? Which will be going this direction. Let me just try to trace it. I can also have F cos of theta. So what you then see is that torque looks at the rotational moment of a force, right? So it looks at the rotational moment of a force, sort of like the effect of a force in causing rotation. So if you look at the force, we can see that the component F sine theta is the one that produces a rotation about the central point. The F cos theta passes through the central point, so it doesn't cause a rotation. So the component which causes the rotation is F sine theta. So from our knowledge of the torque is given by R multiplied by the F. In this case, the component of F that causes the rotation is F sine theta. That is why we have R times F sine of theta. That is where this formula comes from. Fine. Let me go back to what I was trying to explain. So we said that we can multiply. So if you assume that our force is what? Our force is perpendicular here, then we can say that our torque is R times F. Then we know that the force from Newton's laws of motion, F is equals to ma. So I can replace F in this equation with ma. So I'll get my torque is given by R times ma multiplied by, okay, times MA. Then what I know is that if I look at my circular motion, so I want you to keep this equation in your head, and then I'm going to come back to it. I want to explain another concept, the concept of circular motion. So let me explain circular motion right here. So let's look at circular motion. So for circular motion, if we have this circular path, and we have our central point O, and we have the radius of the circle being R, what we know is that if an object is moving at a velocity of v, we know that v is always tangential to the circle, or specifically to the path of the object, right? Path of the object. Then we know that what we know is that this object is changing its direction. So since this object is changing the direction, what we then realize is that it's accelerating, but the acceleration that it's experiencing is an acceleration that is towards the center. So we know that we have an acceleration here, and we call this the radial acceleration. So we have the radial acceleration AR that we have here, which is towards the center, right? Towards the center. And looking at this thing here, I can draw two axes. I can draw a radial axis in the direction of R and a theta axis in the direction of V, right? So at any point, if an object is now here, the radial axis will be here, and then the theta axis will be here in this case, right? So we have seen that the AR is towards the center. And how do we find the AR? We know that the AR, there is a force that keeps this thing from flying away from this circle, right? And from our calculations, we can see that AR is given by V squared over R, which is also equals to omega squared R. I'll explain how it's omega squared R. But before that, one thing that we know is that if we look at this thing, we can see that if an object moves and it reaches this point here, at point 2, it would have covered an angle of theta, right? So having covered an angle of theta, we can say that its rotational speed, which is omega, which is the rotational speed or rotational velocity, omega is given by the change in theta over the change in time, right? That's omega. Change in theta over change in time. And then we can therefore say that our omega is the change in theta per change in time. Then we also know that for an object that is executing circular motion, the V is given by omega R, right? I'm just giving you very important formulas that you should be able to understand and how they come about. So V is omega R, right? So since V is omega R, we can then go and say, okay, you may ask me, how did I get V is omega R? So the way you get V is omega R is, you can look at this concept and say, if this object covers a distance of, if this object covers an angle of theta in time t, I know that the arc length here, if I call it S, arc length here, then S is equals to R theta. From your knowledge of circular geometry, is equals to R theta. So if I then take ds dv, ds dt, I'm sure you guys have done differentiation. You get R is a constant, and then you differentiate theta because theta is what is changing. You get d theta dt. So if you look here, ds dt is the velocity, is equals to r, and then d theta dt, if you look this side, you see that changing in theta over change in time. So if I take the limit of the change in theta over change in time, I get omega is d theta dt. Small change in theta over the small change in time. So d theta dt is omega. So this is how I get my equation. V is equals to r omega. This equation is very, very important. So the tangential velocity of an object that is executing circular motion is given by r times the omega of that object. Good. So let me look at the tangential acceleration, right? So tangential acceleration at in this case. So the at, if I look at what I've written above, I can say that from v is equals to r omega. If I take dv dt, r is a constant, I will have d omega dt. So I'm basically saying d omega dt. So if I am here, I have omega. The omega dt, I know that the change in omega per unit of time. So the change in omega per unit of time is given by alpha. This is what is called alpha. So this one here is called the angular acceleration. So that alpha is angular acceleration. So it's angular acceleration. So that's alpha. So I can also say that the omega dt is also equals to alpha. So I can take the omega dt in this case, in this equation of dv dt. dv dt is a tangential, is given by r multiplied by alpha. So I know that tangential acceleration is alpha r, where tangential acceleration is alpha r, where alpha is angular acceleration, right? And then that the tangential velocity is omega r, where omega is the angular velocity, or the rotational velocity, for instance, rotational or angular, same thing. Okay, so I'm trying to build up to this, that when you are in a circular motion, if you have this as your radius, you know that there is always an AR, which is the radial acceleration, and then you have a tangential velocity, right? And then you say if there is angular acceleration, alpha, then we also have tangential acceleration. Tangential acceleration, which in this case is at. So you can have a situation where there is no tangential acceleration, right? Where there is only a constant velocity around the circle, where in such a case, your v is given by omega r, and then your AR is given by v squared over r, which is also equals to omega r, right? And then you can also say if there is angular acceleration, then you have a tangential, which is equals to alpha r. So these are the three equations that are important for you to remember. So our tangential acceleration can be in the same direction as v, which is a tangential, or it can be either, negative, depending on is the thing decelerating around the circle or accelerating around the circle. Good. Now let's look at the implication of this information to our question. So now let's relate this information to our question. So our question says that we are given this this block here. So I'm going to draw it in another perspective. So it's sort of this way, and then this way. Right. So from there, you can then go and say, when I drop this block here, right? So now we are now looking at the issue of the energy. If you look at this problem, there is the issue of energy. So if I drop this block from this distance here where it was, and I drop it down to this distance here, at a distance of d, what I see is that there is a change in potential energy, right? So this change in potential energy is converted to what? To kinetic energy, right? So I can safely say that the change in potential energy, which in this case is gravitational, is given by the change in kinetic energy. Okay. And then from there, we can go and look at our energy changes. So how do we find the change in potential energy in this case? So a change in potential energy, which is gravitational, is given by the mgh in this case. So our mass in this case is mb, and then our gravity, our h is d. Now let's look at the change in the kinetic energy. The change in the kinetic energy is in two parts, because this object here, when it drops down, it gains kinetic energy, but it also rotates the wheel. So since it's rotating the wheel, we know that the wheel is going to get rotational kinetic energy, right? So this kinetic energy is made up of the K linear kinetic energy and the K rotational kinetic energy. So the linear kinetic energy, we know that it's half of m v squared, and then we want to talk about this rotational kinetic energy. How do we find it, right? So let's talk about rotational kinetic energy. Rotational kinetic energy. So rotational kinetic energy, if you remember, when I was explaining, I looked at this, I said to you, I'm gonna leave you a bit with this information, where I said torque is given by RMA. If I go back here, and the torque is given by RMA. And if you remember, I said to you, so if I'm looking at this circular thing here, okay, let me draw it here. If I have an object which is executing circular motion, right? And my object is here, executing circular motion. What I know is that there is a force which is pushing it to execute circular motion, but the important point is its acceleration in the tangential direction, right? Is what we have discussed before. We said this AT is alpha r, right? So I can come and replace RM, and then I put alpha r, right? This alpha r, we discussed about it in the previous slide. And then I can then say my torque is therefore equals to, I can take out r and m, so I can get mr squared alpha, right? So this mr squared here is what is called the moment of inertia. Moment of inertia. So our moment of inertia in this case is the mr squared, right? And the units, we know that it's kg square meters, right? So I can say my torque is given by I times alpha. So if you compare this equation here to the equation of what? To the equation of F, is equals to ma. You can see that the mass when you are in circular motion is represented by the moment of inertia, and then the acceleration is represented by the what? By the angular acceleration. So we are looking at circular, and we are looking at linear, right? So in circular motion, the force is equivalent to the torque. Then the mass is equivalent to the moment of inertia. And then the acceleration is equivalent to the what? To the angular acceleration, right? Good. Then, if we then want the rotational, so we said the kinetic energy linear is given by half mv squared, right? And the velocity, we saw that in angular motion, we said we have the angular velocity omega is our angular velocity, right? So we can replace and say it's half of the velocity in this case is omega squared. What is our mass? Our mass when we're in circular motion, we said it's I, the moment of inertia. Therefore, we can conclude that K rotational is given by half I omega squared. Okay, this is K rotational, and K linear is half mv squared. Okay, good. So now we can then use that information to do our calculation now, because we said for us to do the calculation, we want the change in the potential energy, gravitational in this case, should be equal to the change in the kinetic energy, the linear one, plus the change in the kinetic energy, the rotational. And then we have already found our change in the gravitational potential energy, which is mb times gd. So we have mb gd is equals to the change in the linear kinetic energy is half mv squared, then plus the change in the rotational kinetic energy in this case is half I omega squared, right? Remember that from what we discussed, omega is, V is equals to omega r, which means omega is V over r, right? So we want to take this and put it in this equation because we want to make V the subject of the formula. They're asking us to find V, right? So we have mb times gd is equals to half. This m here is the mass of the block because the block is the one executing what? Executing linear motion. So it's m of the block times v of the block squared, in this case, plus half I has been given in this problem. Id is half md multiplied by rd squared. So just to talk about the issue of the rotational inertia. Usually, the rotational inertia you are given, or you can calculate it. So the way you find the rotational inertia is that usually there are tables where you are given different shapes and their rotational inertias. For instance, if you have a cylinder which is solid, you know that its rotational inertia I will be half mr squared. But if you have a cylinder that is hollow, where there's nothing inside and the whole mass is concentrated outside, its inertia is I is equals to mr squared. So you just have to deal with each different shape has a different what? Has a different rotational inertia. And rotational is because rotational inertia is basically the resistance of an object to change its angular velocity. So basically, its resistance to be rotated. So, for instance, for this one here, we know that our for this formula. Sorry, I see someone saying that my sound is not good. Can everyone hear me before I proceed, please? Can you guys indicate that I'm still audible? Can you guys please indicate? So the person who has said they can't hear me, can you please try maybe to check your sound, maybe the problem, maybe your network or something? Okay, I'll proceed. So, okay, good, thank you. So if our axis of rotation is through the center, that's when we get what? That's when we get half mr squared. But if our axis of rotation was not through the center, was, let's say for instance here, our formula was going to change altogether. So we have to understand that the I depends on the axis of rotation. How is our object being rotated? And if you can look at your textbook, you will see that there are different formulas. You can even look. You can even look at Google. Just search the rotational inertia of different objects. You'll be able to see the rotational inertia of a rod, of a cylinder, of a sphere. All those things, they are there. Good. So let me remove this one and proceed with the calculation. So we are here. So we're now saying half I. In this case, our I is given as the half of the md rd squared, right? And then our omega squared, we said omega is equals to v over r from this formula here. Therefore, we can put v of the block over rd squared. And then we can get our mb times gd is equals to half of mb multiplied by vb squared plus 1 over 4 of md. And then rd and rd, they cancel out because rd squared over rd squared multiplied by vb squared in this case. And then we can then take, let's say we take, if we multiply both sides by 4, we get 2 mb multiplied by gd is equals to, this one will be 2 mb vb squared plus md vb squared. And then from there, I can factor out vb squared. Then I'll be left with 2 mb plus md. Then on this side, I will have 2 mb multiplied by gd. Then I make vb the subject of the formula. So I will have my vb squared is given by 2 mb g and d divided by 2 mb plus md. Therefore, your vb is given by the square root of 2 mb gd divided by 2 mb plus md. Do you guys understand what we have done here? This is our answer. Any question here? Sorry, it's supposed to be 4. Sorry, remember multiply by 4. Okay. It's supposed to be 4. Yes, let me just correct something before I proceed. It's supposed to be 4 here.
Oh, okay.
Yes. Yes, you can ask, please. Was that your question? Sorry, can you just indicate that were you asking about the 4? Yes, that was a mistake which I made. Okay, I'll assume that that was your question. Okay, good. Guys, did you understand what we did here? So I have discussed many concepts here, and I hope that you were able to understand them. So in one question, I've discussed many things. So in one question, I discussed the issue of circular motion. I've discussed how do we get our formulas for the what, for the velocity and the relationship to the angular velocity. How do we find our radial acceleration? How do we find our tangential acceleration? And I also discussed the issue of the energy and rotational energy. And I discussed with you how do we relate the torque to the linear force, and then how can we then look at that information and put it in the formula for the linear kinetic energy for us to be able to find the rotational kinetic energy, which in this case we have found that rotational kinetic energy is half I omega squared. And then we then solved our question by just substituting our values. Any question here before we go to the next problem? Guys, please ask your questions. You won't have another chance to ask someone to answer you. And I'm here to answer your questions. I'm not running anywhere. I'm here to answer the questions. So if you have not understood something, please just unmute yourself and ask me a question, or you can type in the chat box and then I'll answer you. Let's engage. I'll wait for 30 seconds if there's any question before I proceed to the next problem.